July 5, 1943. Kursk Salient, Soviet Union. 200 newly rebuilt Panther tanks from Panther. Regiment von Lauet of the 39th Panzer Regiment stood ready for their first major engagement, what would become the largest tank battle in history. That morning, 184 Panthers were fully operational, representing Germany's latest innovation, a medium tank equipped with heavy tank armor and firepower that intelligence reports predicted would transform armored warfare. Within 48 hours, only 40 remained in action. Within 2 weeks, operational readiness dropped to just 16%. The Panther's disastrous debut at Kursk revealed a deep contradiction in German tank engineering that Allied intelligence would spend the next 2 years carefully documenting. A clash between impressive specifications and disastrous mechanical reliability that would influence the course of the war. The Panther was born from Germany's urgent response to the Soviet T-34, a tank that had stunned German forces when it appeared in the summer of 1941. The T-34 combined sloped armor, a powerful 76mm gun, wide tracks for maneuverability, and mechanical simplicity into a design that rendered the Panzer III and IFOI obsolete. In reaction, the German Army Weapons Department issued requirements for a new medium tank in November 1941. The PIV design contest between Maschinenfabrik, Augsburg-Nürnberg, MAN, and Daimler-Benz ended with Mann's proposal being chosen in May 1942. Production began in January 1943 with the AUSF-D model, followed by the AUSF-A in August 1943 and the AUSF-UG in March 1944, continuing until the war's end. On paper, the specifications were remarkable, showing real advances in armor protection and firepower integration. At a combat weight of 45 metric tons, the Panther stood between American medium tanks of about 30 tons and Germany's heavy Tiger Rahmen at 57 tons. This intermediate class was meant to combine heavy tank performance with medium tank mobility and lower production cost. The frontal armor, 80mm thick and sloped at 55 degrees, offered protection equivalent to roughly 140 mm of vertical armor due to the physics of sloped surfaces deflecting projectiles. Borrowed from the T-34's design, this concept was a major improvement over earlier German tanks with flat armor plates. Side armor of 40 mm gave some defense against light anti-tank weapons and autocannon fire, but remained vulnerable to all Allied tank guns at normal engagement distances. The main armament, AT-75mm K42L70 gun, was the most powerful tank-mounted weapon in regular service during 1913, 1943-44. The L-70 denoted a barrel length, 70 times the gun's caliber, producing a high muzzle velocity. At 925 ms with standard armor-piercing rounds, it could penetrate any Allied tank through 1944. At 1,000 meters, it could pierce 120 millimeters of armor, enough to defeat any Allied tank frontally. Even at 2,000 meters, it could still destroy a Sherman, while the Sherman's gun couldn't reliably penetrate the Panther's frontal armor at that distance. This enormous advantage in engagement range gave Panther crews the theoretical ability to destroy opponents before coming under effective return fire, core to German tank doctrine. The Maybach HL230P30 engine represented sophisticated German automotive design adapted for military use. This water-cooled 12-cylinder gasoline engine in a 60 V configuration displaced 23.1 liters and weighed 1,200 kilograms. It produced 700 metric horsepower, about 690 imperial, at 3,000 RPM, though in practice was limited to 680 HP at 2,500 ppm to reduce wear. This yielded a power-to-weight ratio of 15.6 HP per ton, typical for tanks of similar mass. The engine required high-octane gasoline, minimum 74 octane, which Germany struggled to produce in sufficient quantities from synthetic fuel plants. The AK-7-200 transmission was an advanced design, providing 7 forward and 1 reverse gear for flexible engine speed selection. However, the Panther's 45-ton weight exceeded its design tolerance, placing heavy strain on the transmission and causing frequent failures. Overheating of transmission oil was a chronic issue, especially during long cross-country movements or combat requiring rapid gear changes. The cooling system often proved inadequate, leading to thermal breakdowns and accelerated wear of components. Maximum road speed was 46 km/h, comparable to other medium tanks, while cross-country speed averaged 25 km/h under good conditions. Range on roads reached 260 km under ideal maintenance, while off-road range dropped to about 100 km due to high fuel consumption and mechanical stress. With a 730-liter fuel capacity, the Panther required frequent refueling, creating severe logistical demands that German supply lines often couldn't meet. Fuel consumption averaged 2.8 km on roads and 7.3 km off-road, meaning a full fuel load allowed roughly 100 km of cross-country travel. These figures made the Panther theoretically superior to any Allied tank of its time. Its sloped frontal armor could withstand hits from American 75mm guns at nearly all combat ranges, while its long-barreled 75mm could destroy Shermans from over 2,000 meters away, beyond the range of return fire. British armor commanders in Normandy later called the Panther the finest tank in Europe, based on firepower and protection alone. German propaganda hailed it as proof of Aryan technical supremacy, a weapon that would reclaim the Eastern Front and repel the coming Allied invasion. Reality struck immediately at Kursk. German records detailed the disaster with cold precision, confirming Soviet reports that German officials had dismissed as exaggeration. On July 5, 1943, 184 Panthers were ready for battle from the 200 delivered to Regiment von Lauet between June 23 and June 29. The week before the battle was spent on final checks, repairs, and crew familiarization. Morale was high, though veteran mechanics warned that the Panthers hadn't been properly tested. Crews praised their new tanks' firepower and protection, confident these advantages would ensure victory. By July 7th, after only 2 days of combat, just 40 Panthers remained functional. This catastrophic 65% loss rate resulted mainly from mechanical failures, not enemy fire. Final drives broke under the stress of muddy terrain. Transmissions overheated and seized. Engines caught fire from faulty fuel systems. Cooling leaks caused overheating and engine destruction. Tracks snapped under load, and suspension arms fractured under impacts that lighter tanks could endure. Maintenance crews, overwhelmed and short on spare parts, couldn't keep up with the rate of breakdowns. A report dated July 20, 1943, issued after the offensive failed, recorded the situation precisely. 41 Panthers operational, 85 repairable in the field with parts and time, 16 needing factory repair, 56 destroyed by enemy action, and 2 lost to non-combat engine fires. The end of July operational rate, 16%, was disastrous. Hitler demanded explanations, leading to inquiries that blamed insufficient testing instead of the design flaws at the core of the problem. This pattern repeated wherever Panthers were deployed. Operational availability. The percentage of tanks ready for combat averaged between 35 to 40% during 1943. Post-war German records confirm an average of 37% across all fronts by year's end. A nominal battalion of 96 tanks typically had about 35 operational at any given time, with the rest under repair or awaiting parts. This made sustained offensives impossible, as mechanical losses outpaced repairs. Availability improved somewhat in 1944 to about 54%, but the Panther never reached the reliability German doctrine required. Some periods showed better performance thanks to improved training and logistics, not design fixes. Records from September 1944 on the Eastern Front show 75.8% availability, 552 operational of 728 total. During the Battle of the Bulge, 71.3% were operational, 336 of 471. Even these improved rates fell short of the 80 to 90% reliability demanded for prolonged offensives. They also depended on ample supplies and preparation, conditions increasingly rare as Allied pressure mounted and German logistics deteriorated. The comparison with Sherman operational availability reveals the cumulative impact of reliability differences. While precise documentary confirmation of Sherman's 70 to 80% availability has not been located in all accessible sources, multiple authoritative analyses describe the Sherman as having superior reliability and superior mechanical reliability compared to the Panther. The operational reality visible in unit after action, reports and divisional strength summaries, consistently shows American armored divisions fielding higher percentages of their authorized tank strength than German Panzer divisions throughout 1944 and 1945. This availability differential, approximately 30 to 45 percentage points favoring American forces, compounded the already substantial American advantage in total production numbers to create battlefield superiority that German tactical skill and technical specifications could not overcome. The core problem lay in a fundamental design contradiction. The Panther was conceived as a 35-to-9 medium tank, but the addition of heavy armor and a powerful gun increased combat weight to 45 tons, a 28% overload. This weight exceeded the design parameters of virtually every mechanical component, creating cascading reliability problems that no amount of field modification could fully solve. The most catastrophic failure point was the final drive, the mechanism that transferred power from the transmission to the drive sprockets that moved the tracks. The French Army provided the most comprehensive post-war analysis of Panther reliability. France operated a full battalion of 50 Panthers through 1947 as part of the 5,003rd Tank Regiment, giving French forces almost twice as much operational time with Panthers as any German formation had achieved during the war. The official French Ministry of War report, titled Le Panther, published in 1947, stated explicitly that the truly weak spot of the Panther is its final drive, which is of too weaker design and has an average fatigue life of only 150 kilometers French. Examination of abandoned Panthers found in Normandy in 1944 revealed that half showed evidence of final drive breaks. This was not combat damage, but mechanical failure from normal operation. The metallurgical analysis conducted by French and American technical teams after the war revealed the underlying cause. German steel production in 1944 reached 28.5 million tons through incorporation of conquered territories, including French Alsace and Czech Sudetenland. Production had peaked at 34.66 million tons in 1943. However, Germany had lost access to critical alloying metals necessary for high-quality steel production. Allied bombing of the Narban molybdenum mine in Norway in 1943 eliminated Germany's primary source of this critical element. Molybdenum increases steel's resistance to heat and fatigue. Nickel, another critical alloying element, became increasingly scarce as the war progressed, and Germany lost access to international markets. Soviet technical trials of captured Panthers found armor plates containing between 0.6 and 1.7% nickel in various locations. German sources described final drives as made of low-grade steel with low core strength of material used. While these specific percentages of deficiency could not be verified in all accessible primary sources, the general material degradation is extensively documented. The combination of design overload and material quality decline created a catastrophic reliability problem. Final drives that should have lasted thousands of kilometers under normal conditions failed after as little as 150 kilometers of operation. Transmission failures, engine problems, and suspension damage occurred at rates far exceeding those of Allied tanks. The production statistics tell the story of Germany's strategic error. Germany produced approximately 6,000 Panthers between January 1943 and April 1945. The breakdown by variant shows 842 AFD from January to September 1920 wider 943 2200 Alpha A from August 1943 to August 1944. Approximately 2,161 AFG from March 1944 to April 1945, plus 329 Befehlspanzer command variants. Peak frontline strength reached 2.34 tanks on September 1, 1944. Production. Cost per Panther was 117,100 Reichs. Marks without armament and radio compared to 250,800 rich marks for the Tiger I and 103,462 rich marks for the Panzer IV. The United States produced 49,324 Sherman tanks in 11 plants. Between February 1942 and July 1945, representing the most successful tank production program in military history, measured by total units produced and sustained over time. The Sherman, officially designated M4 medium tank, evolved through multiple variants using different engines, transmissions, and hull configurations while maintaining commonality of critical components that simplified logistics and maintenance. The most common variant used the Continental R975 radial engine producing 400 horsepower licensed from the Wright R975 Whirlwind aircraft engine. This 9-cylinder air-cooled radial engine originally designed for aircraft proved remarkably reliable in tank application. Despite initial skepticism about adapting aircraft engines to ground vehicles, the Sherman weighed 30 metric tons in combat configuration, 15 tons lighter than the Panther. This lower weight reduced stress on all mechanical components, improving reliability and extending service life. The main armament on most Shermans was a 75 mm M3 gun, a competent weapon adequate for destroying most Axis tanks through 1943, but increasingly inadequate against heavily armored German tanks like the Panther and Tiger from 1944 onward. Maximum armor of 76 mm on the frontal hull, mounted vertically rather than sloped, provided less protection than Panther armor, but proved adequate against most German tank guns at medium ranges. Maximum road speed of 40 km per hour, slightly slower than the Panther, provided adequate tactical mobility for American armored doctrine that emphasized sustained operations over maximum speed. The Sherman's true superiority lay not in specifications, but in reliability, maintainability, and production efficiency. The Continental R975 engine required minimal maintenance compared to the complex Maybach engine in the Panther. Oil changes every 250 hours of operation versus every 100 hours for the Panther reduced maintenance burden. Air cooling eliminated the complex cooling system that plagued Panther operations, removing an entire category of potential failures. The transmission, though less sophisticated than the Panther's 7-speed design, proved remarkably reliable and could be replaced in field conditions within 8 hours by trained maintenance crews. Final drives, conservatively designed with adequate strength margins, rarely failed under normal operating conditions. Suspension components using vertical volute spring bogies instead of interrolled road wheels could be maintained and repaired quickly without extensive disassembly. Production efficiency gave the Sherman overwhelming numerical advantages. The average Sherman required approximately 10,000 man-hours to produce in established factories operating at peak efficiency. By 1944, the Panther required approximately 15,000 man-hours, 50% more labor for each unit. American factories used advanced production techniques, including extensive sub-assembly, standardized components across variants, and progressive assembly methods that minimized skilled labor requirements. German factories relied more heavily on skilled craftsmen to fit components that were less precisely standardized, increasing production time and costs. American production peaked at over 2,000 Shermans per month during mid-1944. German Panther production peaked at approximately 380 units per month, less than 1/5 if American output. Despite Germany dedicating proportionally more industrial capacity to tank production. The operational consequences of these production differentials compounded over time. American armored divisions that suffered tank losses in combat received replacement vehicles within weeks, sometimes within days, if supply lines were functioning normally. Crews knew that destroyed tanks would be replaced, reducing psychological stress and encouraging aggressive tactics. German panzer divisions that suffered losses waited months for replacements, if they received any at all. Crews knew their Panthers were irreplaceable, creating caution that undermined German tactical doctrine requiring aggressive action. By late 1944, many German panzer divisions operated at less than 50% authorized tank strength, not from combat losses alone, but from inability to replace losses at rates matching attrition. Yet the Sherman won the war, while the Panther lost it, because specifications written on paper matter less than availability on the battlefield. The fundamental principle that determined victory was not which tank had better armor or firepower, but which tank was actually present and operational when needed. The Sherman achieved operational availability rates between 70% and 80% throughout the war. Though direct documentary confirmation of this precise figure has not been located in accessible sources, multiple authoritative sources describe the Sherman as having superior reliability and superior mechanical reliability compared to the Panther. The operational availability differential, approximately 30 to 45 percentage points in favor of the Sherman, meant that American armored divisions consistently fielded far more operational tanks than German panzer divisions, despite comparable nominal strength. The maintenance burden imposed by the Panther consumed resources Germany could ill afford. Each Panther battalion required specialized recovery vehicles, mobile workshops, and stocks of spare parts that dwarfed the logistics footprint of a Sherman battalion. A typical American armored division required approximately 200 trucks dedicated to armored vehicle maintenance and supply. A German panzer division equipped with Panthers required approximately 400 trucks for the same function. Trucks that Germany did not possess in sufficient quantities and could not fuel even if possessed. The fuel consumption differential compounded the problem. A Sherman battalion conducting a 100-kilometer road march consumed approximately 14,000 L of gasoline. 14,000 L of gasoline. A Panther battalion conducting the same march consumed approximately 35,000 L, assuming all vehicles completed their march without mechanical failure, which historical records suggest was unlikely. By late 1944, Germany was producing approximately 6 million tons of synthetic fuel annually, barely 1/10th of American petroleum production. The psychological impact on German forces of their supposedly superior equipment's mechanical fragility emerges clearly from captured documents and post-war interviews. German tankers learned through experience that their Panthers were unreliable. The knowledge that their vehicle might break down at any moment, stranding them deep in enemy territory, far from recovery assets, created caution that undermined the aggressive exploitation of tactical success that German doctrine required. Commanders hesitated to commit Panthers to bold maneuvers because they feared mechanical failure more than enemy fire. This psychological burden imposed by flawed engineering contributed to German tactical paralysis during the final year of the war. The Battle of the Bulge in December 1944 demonstrated these problems at operational scale. German forces committed 471 Panthers to the offensive, with 336 operational at a 71% availability rate that represented exceptional preparation. Within 1 week, mechanical failures had reduced operational strength by approximately 1/3, not from combat losses, but from breakdowns on the advance. Panthers abandoned for mechanical reasons littered the roads through the Ardennes. German recovery units, already stretched thin, could not retrieve all disabled vehicles before American forces recaptured the territory. The offensive failed not primarily from lack of fuel, as popular accounts suggest, but from the systemic unreliability of German armored vehicles that limited operational tempo, even when fuel was available. The contrast between German and American approaches to military technology extended beyond tanks to virtually every category of equipment. German small arms were magnificently engineered, but expensive and slow to produce. The MP-40 submachine gun required approximately 10 hours of skilled machinist time to manufacture. The American M3 grease gun required less than 3 hours of semi-skilled labor. Both weapons fired the same caliber ammunition at similar rates. The American weapon was uglier, crudder, and vastly more practical for mass production. This pattern repeated across artillery, aircraft, vehicles, and every category where American pragmatism confronted German perfectionism. The philosophical difference reflected fundamentally different understandings of modern industrial warfare. German military culture rooted in Prussian traditions emphasizing individual excellence and technical sophistication could not adapt to the reality that 20th-century warfare rewarded mass production over individual perfection. The German army entered World War II with doctrines developed from World War I experience, emphasizing breakthrough and exploitation through concentrated armored formations, employing technically superior equipment operated by highly trained elite forces. This doctrine achieved spectacular successes in Poland and France against enemies who were unprepared and poorly organized, against the Soviet Union and the United States, nations capable of absorbing initial defeats and mobilizing vast industrial resources. The German approach failed catastrophically. American military doctrine, informed by different historical experience and different industrial capacity, embraced mass production and logistical sustainability as primary virtues. The Sherman tank exemplified this philosophy. It was not the best tank by any specification. It was the best tank that American industry could produce in sufficient quantity, that American logistics could support in global operations, that minimally trained crews could operate effectively, and that field maintenance units could keep operational under combat conditions. These virtues, dismissed by German engineers as evidence of technical inferiority, proved decisive. The final accounting reveals the magnitude of Germany's strategic error. 6,000 Panthers hamstrung by mechanical unreliability achieved operational effectiveness roughly equivalent to 3,000 reliable tanks. The resources consumed by Panther production could have produced approximately 9,000 Panzer IV tanks. The Panzer IV, while inferior to the Panther in specifications, was mechanically reliable and adequate for combat against all but the heaviest Allied armor. 9,000 Panzer IVs, actually available for combat rather than awaiting maintenance, would have provided far greater military value than 6,000 temperamental Panthers. This conclusion is not speculation, but mathematical certainty derived from operational availability statistics and production cost analysis. The human cost of German over-engineering extended beyond logistics to training and doctrine. Panther crews required extensive specialized training to operate and maintain their complex machines. This training took months that Germany increasingly could not afford. Sherman crews could be trained to basic proficiency in weeks, and the mechanical simplicity of the Sherman meant that crew survivability was higher because catastrophic mechanical failures were less likely to trap crews in disabled vehicles under fire. German tank crew casualties from mechanical failures that prevented escape from damaged vehicles were proportionally higher than American casualties from the same cause. Though precise comparative statistics are difficult to establish from available records, the British Army's experience with captured Panthers provided additional confirmation of German reliability problems. British forces tested Panther No. 433 amid production AF, a variant in mobility trials in the United Kingdom during 1944. The British technical description of this specific tank was completed in late May 1944. British reports confirmed German findings about final drive weakness and noted additional problems with the interled road wheel suspension that German designers had implemented to improve cross-country performance. The overlapping wheel design, featuring wheels mounted on overlapping axles rather than individual bogies, provided superior weight distribution and ground pressure reduction. This allowed the Panther to traverse soft ground more effectively than tanks using conventional suspension designs. The theoretical advantages were genuine and measurable in controlled testing conditions. The practical reality under combat conditions told a different story. Mud accumulated between the overlapping wheels during cross-country movement. In winter conditions, common across much of the Eastern Front and Northern Europe, this mud froze solid overnight. By morning, the suspension was locked, immobilizing the tank until crews could chip away the ice or wait for temperatures to rise sufficiently for melting. This process could take hours under favorable conditions, days under severe winter weather. German tankers in Russia learned to avoid muddy terrain whenever possible, limiting their tactical flexibility to avoid suspension immobilization. Maintenance requirements for the interled suspension exceeded those of conventional designs by an order of comagnitude. Changing an outer road wheel on a Sherman required approximately 30 minutes with proper tools. Changing an inner road wheel on a Panther required removing up to 8 outer wheels first, a process that could consume an entire day, even with experienced maintenance crews and proper equipment. Under field conditions with improvised tools and time pressure from tactical situations, this maintenance burden became prohibitive. German maintenance units, already overwhelmed by final drive replacements and transmission repairs, faced additional workload from suspension maintenance that conventional designs would have avoided. British armor officers, after extensive evaluation of captured Panthers, concluded that despite superior armor and firepower, the Panther's mechanical complexity made it unsuitable for British operational requirements. British tank doctrine emphasized reliability and maintainability, precisely because British military planners understood that operational availability determined battlefield effectiveness more than individual technical specifications. The production timeline for Panthers revealed additional strategic failures in German planning. Hitler personally intervened in Panther development multiple times, demanding increased armor protection and more powerful armament, while simultaneously demanding accelerated production schedules. These contradictory requirements created exactly the problems that materialized at Kursk. The Panther was rushed into production before adequate testing could identify and resolve the final drive weakness. Normal vehicle development includes extensive durability testing, where prototypes are subjected to conditions exceeding expected operational use to identify failure points before mass production begins. The Panther program, compressed by Hitler's demands, skipped or abbreviated these crucial testing phases. The result was a weapon system that failed catastrophically when exposed to actual combat for conditions exactly the outcome that proper testing would have prevented. The organizational culture within the German military-industrial complex compounded these problems. German engineering culture emphasized technical excellence and sophisticated solutions to complex problems. This culture produced genuine innovations, including the first operational jet fighter, the first ballistic missiles, advanced submarine designs, and numerous other technological achievements. However, this same culture struggled with the practical requirements of mass production and field maintenance. German engineers designed weapons for ideal conditions, assuming proper maintenance by trained technicians using specialized tools in well-equipped facilities. American engineers designed weapons for realistic conditions, assuming field maintenance by minimally trained personnel using improvised tools under combat stress. These different design philosophies produced the Sherman and the Panther, two tanks that embodied opposite approaches to military engineering. The training burden imposed by Panther complexity extended beyond crews to include maintenance personnel at every level. A Sherman battalion required approximately 40 maintenance personnel with basic mechanical skills. A Panther battalion required approximately 80 maintenance personnel, including specialists trained in complex transmissions, specialized final drive procedures, and sophisticated engine maintenance. Germany could not produce these trained specialists fast enough to meet demand. By late 1944, Panther battalions routinely operated with maintenance units at 50 to 60% of authorized strength, further reducing operational availability. Untrained or minimally trained mechanics attempting complex repairs resulted in additional damage, creating cascading maintenance problems that reduced availability even further. The fuel logistics challenge created by the Panther cannot be overstated. The Panther cannot be overstated. 2.8 L per kilometer road consumption, while accurately stated in specifications, assumed optimal conditions with properly maintained engines and transmissions. Actual field consumption often exceeded 3 L per kilometer due to mechanical problems that reduced efficiency. A Panther traveling from Germany to the Eastern Front consumed its entire fuel load multiple times. During the journey, Germany lacked sufficient fuel trucks to support large-scale Panther deployments. Panzer divisions were frequently immobilized, not by enemy action, but by inability to deliver fuel to forward units. The strategic impact of this fuel shortage shaped German defensive strategy during 1944. German commanders knew their Panthers could not sustain mobile operations because fuel supply could not support sustained movement. This knowledge forced defensive tactics that surrendered initiative to Allied forces, exactly the opposite of German doctrine that required aggressive maneuver and exploitation. American forces captured their first Panthers in Tunisia during May 1943, though in limited numbers. The systematic capture of Panthers in operational condition occurred primarily during the Normandy campaign, beginning June 1944. American Ordnance units established enemy equipment evaluation teams attached to field armies specifically to identify, recover, and analyze captured German vehicles. These teams included mechanical engineers, metallurgists, and intelligence specialists trained to extract maximum information from captured equipment. The intelligence gathered from these teams informed tactical bulletins distributed throughout American forces, providing tank crews and infantry units with specific information about Panther vulnerabilities and recommended engagement tactics. American forces captured multiple Panthers in France and Germany during 1944 and 1945, with systematic recovery and analysis procedures that evolved throughout the campaign. It is believed that 14 captured Panthers were shipped to the United States for technical evaluation, though definitive shipping records have not been located in accessible archives. Most captured Panthers were scrapped after testing, with only 5 Panthers surviving in America today as museum pieces. Aberdeen Proving Ground in Maryland tested captured German vehicles during World War II with documentation, confirming that for more than a year captured enemy vehicles had been arriving at the facility by January 1944. Panthers were eventually displayed at Aberdeen's Ordnance Museum collection, confirming United States possession and testing of multiple examples. However, specific technical reports from Aberdeen detailing 1944 Panther test procedures and results have not been located in fully accessible archives, leaving details of specific test protocols unclear from available documentation. The intelligence analysis of Panther capabilities and weaknesses influenced American tactical doctrine throughout the final 18 months of the war in Europe. Understanding that the Panther's 75 mm gun could destroy Sherman's, at ranges exceeding 2,000 meters, while Sherman's 75 mm guns could not reliably penetrate Panther frontal armor at any range. American doctrine emphasized tactics that exploited Panther weaknesses rather than confronting its strengths. Tank destroyer doctrine built around the 3-in gun mounted on M10 Wolverines and later the 90mm gun on M36 Jackson tank destroyers provided the primary anti-Panther capability. These vehicles, more lightly armored than tanks but mounting more powerful guns, were positioned in defensive positions where they could engage Panthers at extended ranges or from ambush positions targeting vulnerable side armor. Infantry anti-tank tactics evolved rapidly as American forces gained experience fighting Panthers. The 2.36-in bazooka, effective against earlier German tanks, proved inadequate against Panther armor. Tactical bulletins distributed to infantry units emphasized that bazookas should target side and rear armor at close range, not frontal armor. Infantry units learned to allow Panthers to pass their positions, then engage from behind where armor was thinnest and ammunition stowage was vulnerable. Close assault tactics using satchel charges and sticky bombs required courage, bordering on recklessness, but proved effective when properly executed. American infantry casualties from Panther engagements remained high throughout the war, but the kill ratio improved steadily as troops learned and applied effective tactics distributed through training and tactical intelligence bulletins. Artillery became the most effective. American counter to Panthers not through direct fire, but through indirect fire and mobility denial. Forward observers learned to call artillery fire on disabled Panthers that German recovery units could not immediately retrieve. American artillery doctrine emphasized rapid response to fire missions with battalion-level artillery capable of delivering concentrated fire within 5 minutes of observer request. Panthers disabled by mechanical failure, immobilized by terrain obstacles, or simply stopped to engage American forces became targets for artillery concentrations that destroyed tanks or forced crews to abandon vehicles. The psychological effect on German tankers was significant. Panther commanders learned that stopping for any reason invited artillery fire that their armor could not protect against. This knowledge created pressure to keep moving. Exactly the operational tempo that Panther mechanical reliability could not sustain. Air power provided additional capability against Panthers, though direct air-to-ground attacks on individual tanks proved less effective than popular accounts suggest. Tactical aircraft armed with rockets and bombs achieved modest success rates against moving tanks. The primary value of air power against armored forces was interdiction, attacking supply columns, fuel trucks, repair facilities, and other supporting infrastructure that sustained Panther operations. A Panther without fuel, spare parts, or recovery capability was as useless as a destroyed Panther. American air superiority over European battlefields by mid-1944 meant that German armored forces moved primarily at night to avoid air attack, further straining mechanical reliability and complicating logistics. The cumulative effect of air interdiction on German armored operations exceeded the direct destruction of tanks through ground attack. The systematic intelligence analysis conducted by American and British technical teams examining captured Panthers produced detailed reports that were distributed through intelligence channels to commanders at division and corps level. These reports included specific technical specifications, armor thickness measurements from multiple angles, penetration data for various weapons at various ranges, photographs of vulnerable points, and recommended engagement tactics. Company-level officers received simplified tactical bulletins highlighting key vulnerabilities and recommended techniques. This intelligence distribution system, mundane and unglamorous compared to dramatic battlefield actions, shaped tactical decisions that saved American lives and accelerated German defeat. The value of this intelligence work is difficult to quantify precisely, but emerges clearly from after-action reports that document how American units modified tactics based on distributed intelligence about German equipment capabilities and vulnerabilities. The broader strategic lesson from Panther development and deployment extends beyond World War II, War II, to shape American defense procurement for decades. The principle that the best weapon system is the one that is actually available when needed rather than the one with the most impressive specifications became foundational to American military planning after World War II. This philosophy directly contradicted the approach that had dominated military procurement in the 1930s, when specifications emphasized theoretical maximum performance, with less attention to reliability and maintainability. The Panther's failure, analyzed in detail by post-war studies, validated the alternative philosophy that adequate performance sustained over extended operations defeats superior performance that cannot be maintained under field conditions. This principle informed development of every major American armored vehicle designed after World War II. 2. The M48, patent tank entering service in 1952, emphasized mechanical reliability and ease of maintenance as primary design. Requirements equal to armor and firepower. Lessons learned from Panther analysis influenced transmission design, final drive engineering, suspension systems, and maintenance accessibility. The M60 tank entering service in 1960 continued this emphasis on reliability and maintainability. The M1 Abrams tank entering service in 1980 represents the culmination of this philosophy while incorporating sophisticated technology, including composite armor and a gas turbine engine. The Abrams was designed from the beginning with reliability, maintainability, and logistical sustainability as requirements co-equal with combat performance. This represented the direct rejection of the German approach that had prioritized individual technical superiority over systemic sustainability. The institutional changes within American military procurement following World War II reflected hard-won lessons about the relationship between technical specifications and operational effectiveness. Durability testing became mandatory for all new weapon systems, with prototypes subjected to conditions exceeding expected operational use before production approval. Maintenance procedures were evaluated as rigorously as combat performance. Logistics requirements were calculated and evaluated before production decisions. Supply chain sustainability became a procurement criterion. These changes, revolutionary at the time, are now so thoroughly integrated into military procurement that their origin in World War II lessons about German over-engineering has been largely forgotten. The Panther's failure created the framework for successful American weapon development that continues to present day. Universities teaching courses in engineering management continue to use the Panther as a case study in how not to develop complex systems. The case study examines requirements, creep the process by which additional capabilities are added during development without proportionally increasing the design parameters of supporting subsystems. Business school students study the Panther as an example of how an organization's cultural values can undermine effective decision-making. German military culture valued technical sophistication and engineering excellence, leading to design decisions that produced sophisticated systems unsuited to the operational environment. American military culture valued pragmatism and results, leading to design decisions that produced crude, yet effective systems suited to sustained operations. Neither culture was objectively superior, but American culture proved better adapted to industrial warfare's requirements. The lesson extends beyond military applications into any domain where reliability, maintainability, and sustainability matter as much as raw performance. The comparative analysis of German and American tank production reveals the mathematical inevitability of German defeat once both nations committed to total industrial mobilization. Germany's decision to produce 6,000 complex Panthers rather than 9,000 simpler Panzer IVs represents the kind of strategic error that compounds across an entire military-industrial system. Similar errors occurred in aircraft production, where Germany produced sophisticated fighters requiring extensive maintenance rather than adequate fighters in greater numbers. Artillery production emphasized precision and range at the expense of quantity. Small arms production emphasized quality over manufacturability. Across every category of military equipment, German industry made choices that optimized individual weapon performance while undermining collective force capability. American industry made the opposite choice consistently. The Sherman was adequate, not excellent. The P-51 Mustang fighter was effective, not revolutionary. The M1 Garand rifle was reliable, not perfect. American artillery emphasized rapid production and ammunition abundance over maximum range. This systematic preference for adequacy, sustained over time, proved decisive. By 1944, American forces could afford to lose equipment at rates that would have crippled German forces because American production replaced losses within weeks, while German losses accumulated. American maintenance units could repair damaged equipment quickly because designs emphasized maintainability. American supply chains delivered spare parts, fuel, and ammunition reliably because logistics planning began during weapon design rather than after deployment. These advantages, individually modest, compounded across millions of pieces of equipment and years of sustained operations to create overwhelming superiority. The Panther today represents a fascinating historical paradox that extends beyond simple technical analysis to encompass fundamental questions of culture, doctrine, strategic decision-making, and the nature of modern warfare. It was simultaneously one of the best tanks of World War II in terms of armor protection and firepower, and one of the worst in terms of reliability and operational sustainability. It was a triumph of engineering sophistication that demonstrated German technical capabilities at their peak and simultaneously a disaster of strategic planning that demonstrated the catastrophic consequences of divorcing technical excellence from operational reality. It impressed everyone who saw it, intimidated Allied tankers who faced it in combat, earned respect from enemy armor, officers who evaluated captured examples, and yet disappointed everyone who tried to maintain it under actual combat conditions, far from rear area maintenance facilities with adequate tools and spare parts. The Panther was exactly what Germany did not need at the moment Germany needed it most. Germany needed adequate tanks in overwhelming numbers to replace catastrophic losses on the Eastern Front and prepare for inevitable Allied invasion in the West. Germany produced sophisticated tanks in inadequate numbers that spent more time undergoing maintenance than engaging enemies. Germany needed simple, reliable vehicles that minimally trained crews could operate and field maintenance units could repair. Germany produced complex vehicles requiring extensive crew training and specialized maintenance that consumed disproportionate resources. Germany needed weapons optimized for defensive warfare that could be produced despite shrinking industrial capacity and material shortages. Germany produced weapons optimized for offensive warfare that required vast industrial resources and materials that were no longer available in adequate quantities or quality. These contradictions emerged from German military culture, strategic assumptions, and decision-making processes that proved fundamentally unsuited to the kind of war Germany was fighting by 1943. German military tradition emphasized quality over quantity, technical sophistication over simplicity, and individual excellence over mass production. These values had served Prussia and Germany well in previous conflicts, where wars were decided by relatively small professional armies fighting decisive campaigns of short duration. World War II was not that kind of war. It was a war of industrial attrition, where victory required sustained production over years, where lost equipment and personnel needed rapid replacement, where logistics determined what was possible more than tactics, where systemic sustainability mattered more than individual superiority. American military culture, shaped by different history and different strategic circumstances, proved better adapted to industrial warfare's requirements. American tradition emphasized practicality over perfectionism, results over elegance, and mass production over craftsmanship. The American military was not inherently superior to the German military in training, doctrine, or tactical skill. American advantages lay in industrial capacity, logistics, and philosophical approach to weapon development that prioritized adequacy sustained over time rather than excellence that could not be maintained. These advantages, individually modest, compounded across millions of pieces of equipment and years of sustained operations to create overwhelming superiority that German technical excellence could not overcome. The legacy of the Panther extends to the present day in ways both obvious and subtle that continue to influence military planning, engineering, education, and defense procurement policy. Every American armored vehicle designed since World War II incorporates lessons learned from systematic analysis of captured German tanks. The emphasis on reliability over raw performance, the focus on maintainability and logistical sustainability, the understanding that the best weapon system is the one that is actually available when needed rather than the one with the most impressive specifications. All these principles trace back to intelligence, analysis conducted during and immediately after World War II. These lessons, purchased at a terrible cost in American and Allied lives, saved countless others in later conflicts, where dependable equipment proved decisive. The Panther stands as a lasting reminder to military strategists and defense procurement officials that engineering brilliance, when separated from operational practicality, produces weapons that lose wars even while winning battles. It remains a testament to the truth that in modern industrial warfare, sustained systems outlast isolated superiority over the long course of operations. The tank that now looks imposing in museums, admired for its heavy armor and powerful gun, was defeated by the tank that simply worked in the mud, that could be repaired quickly by field mechanics, and that was actually present when the fighting began. These lessons still resonate in modern defense planning, where technological sophistication must be balanced with reliability, maintainability, manufacturability, and logistical endurance. Engineering students studying the Panther encounter the concept of requirements creep, the dangerous tendency to add new capabilities during development without adequately strengthening supporting systems. They learn the necessity of durability testing before mass production, the connection between design complexity and ease of field maintenance, and that the most elegant technical solution is not always the best when real-world constraints apply. These insights extend beyond the military, touching commercial engineering, infrastructure design, and any field where reliability equals capability. Modern defense planners examining the Panther study how cultural assumptions can distort technical judgment. They learn the importance of matching weapons to actual strategic needs rather than idealized visions of warfare. They see how small reliability differences, when multiplied across thousands of vehicles and months of campaigning, create decisive outcomes. They learn that operational readiness rates matter more than theoretical strength, and that logistics, more than tactics or technology, defines what is truly possible. Such lessons shape modern debates about defense budgets, procurement priorities, and force composition. Statistical analysis of the Panther's record reveals truths that simple narratives often hide. 49,000 Shermans, with 75% availability, meant roughly 36,750 tanks in the field at any given time. 6,000 Panthers, with 40% availability, meant about 2,400 operational tanks. That 15-to-1 difference in real battlefield presence erased the Panther's technical edge. German forces could win single engagements through superior armor and firepower and still lose entire campaigns, even the war itself, because they could not maintain the operational tempo required for victory. Impressive specifications on paper could not compensate for systemic failure to deliver sustained combat capability. The Panther's remarkable downfall teaches far more than its dazzling design ever could, because failure exposes truths that success often hides. Success can be credited to many factors and invites multiple interpretations. Failure, especially the collapse of an advanced system, reveals deep flaws that cannot be dismissed or excused by misfortune. The Panther failed because German strategic assumptions, engineering culture, and procurement systems produced a weapon ill-suited to the nation's actual situation in 1943. That failure, recorded in meticulous German reports and examined carefully by Allied intelligence, remains a timeless lesson about the fragile link between technical excellence and true military effectiveness.